Yeah, shall we?
Yeah.
And I've been looking at hotels like in between here and here, which is literally like your parents' house.
That's amazing.
I think that's the conference hotel we were recommending. It's like the
I'll be almost as close as that. That's so sweet.
Hello, hello, everybody. It is my great pleasure to introduce Dr. Lily Hahn today, who is visiting us from Scripps Institution of Oceanography, where she's currently a NOAA Global Climate Change postdoc, which is an extremely prestigious postdoctoral fellowship to receive, so congratulations. Lily did an undergrad in geology and geophysics at Yale, is that correct? Yeah, and then some research at HUI, and then you went on, at Oslo as well, right? That's where you started getting a little bit interested in the polar climates as well. And then a PhD with Kyle Armour and David Battisti, who many in the room will know, at the other UW. And finally she's seen the light and come to the real UW. I'm learning, right, John? I'm learning. Right. Yeah. A fun fact about Lily is she's currently in the office that I was in at Scripps. So when you think of Scripps, you think of sweeping 180-degree views of the Pacific Ocean. We had the famous canyon view out the back. But as we were reminiscing, as I was reminiscing, less ocean view is more focus on science. So, you know, as you will see, the output that Lily's been able to produce over the last, I don't know, 5, 6, 7 years is absolutely astounding. A lot about why is the Arctic warming so much, Arctic amplification, and working a lot with large-scale models, but also some idealized work. And yeah, she's now sharing my, following in my footsteps. I used to be Ian Eisenman's postdoc before I became faculty member, and so here we see what the next generation of all this work is. I think we have to also thank Rudra for the invitation of Lily. So thanks for that. And with that introduction, please take it away.
Awesome. Thank you so much. That's a very nice introduction. I am in the cave. It's very dark. But yeah, good for research. Yeah, so I'm excited to talk about the role of atmosphere-ocean ice interactions for warming in the Arctic and beyond. And yeah, this is some work from my PhD, working with Kyle Armour, David Battisti, and CC Bitts at the other UW, and then some work from my postdoc this past year, working with Ian Eisenman and Nick Lutzko at the Scripps Institution of Oceanography. I'll start with the role of sea ice for Arctic warming and its seasonality in part 1, and then move a little bit outside of the Arctic to think about the role of the Atlantic Meridional overturning circulation for uncertainty in near future warming. So for this first part, my main question is, how does sea ice impact Arctic warming? And we know that one key effect of sea ice is through the ice albedo feedback. So the schematic is showing that ice is a really bright surface that reflects a lot of the incoming sunlight, and as we warm the climate and lose that sea ice, it's replaced by this darker ocean surface that absorbs a much larger fraction of incoming sunlight. And so that leads to even more warming and more ice melt in this positive ice albedo feedback. And that leads to a lot of extra warming in the Arctic. But we expect sea ice to impact Arctic warming in some other ways besides the ice albedo feedback. I'm going to first show this how some others have shown this ice albedo feedback is important through suppressing it in climate model experiments. So in this Hall 2004 paper, they used a global climate model to perform the CO2 doubling experiment, and they did that. They're showing near surface warming in each season of the year in that model when you allow the surface albedo to adjust under that forcing. Or on the right panel, if you fix the albedo to climatological values so that it can't change in response to CO2 doubling. And that really shows that there's this, you get significantly damped warming if you don't have this ice albedo feedback. So just to highlight the role of the ice albedo feedback for increasing warming in the Arctic. But as I was saying, we expect sea ice to impact warming in other ways, including through other thermodynamic effects like sea ice thermal inertia, and also dynamic effects like sea ice export. So what are these things? I'll give a little background and talk more later. But so the ocean mixed layer is this thick layer of water that's coupled to surface heat fluxes through turbulent mixing, and so it's really slow to respond to a surface heating. It's slow to warm and slow to cool down. It has this large thermal inertia, whereas sea ice acts more, frozen sea ice acts more like land, where it's really quick to warm up and cool down in response to surface heating. It has a very small thermal inertia. So that'll come into play in impacting both the seasonality of Arctic warming and the annual mean warming in the Arctic too. But this is one effect besides ice albedo that might impact Arctic warming. And then another effect are these dynamic effects of sea ice export. So ice gets formed in the Arctic that involves a latent heat release to the Arctic, and then it gets exported out of the Arctic and melts, which requires latent heat uptake. And so the net effect is this latent heat import into the Arctic from lower latitudes that's associated with that sea ice export. So we expect that latent heat import associated with sea ice export to also impact Arctic warming. And I'll talk about that too. Yeah, so in order to try to get at these other non-albedo effects of sea ice, I'm going to run some new experiments that isolate those effects in a warming climate. I'll use this ESM1 climate model with the CAM4 atmospheric model coupled to a slab ocean. And I'm going to run some standard experiments that do have sea ice, and then some experiments that are a little different. They have no sea ice, and I've done that by lowering the freezing point of water, so it can't freeze. It can never form sea ice. But then I've also prescribed monthly climatological surface albedo taken from the ice runs. So our no ice set albedo runs have the same surface albedo, the amount of reflected sunlight, as our ice experiments. So I end up with 4 experiments, 2 with 1850 forcing, this 1850 CO2 conditions, where we have our standard ice experiment, and then we have no ice runs, but with albedo set from those 1850 experiments with ice. And then I have the same under double CO2 forcing. We have ice experiments, and then runs with no sea ice, but albedo taken from the double CO2 run, also under double CO2 forcing. So these no ice set albedo experiments going from a pre-industrial control to a doubled CO2, they have the same changes in albedo and surface albedo as in our ice experiments. But our ice experiments have those albedo changes plus a lot of other stuff, including these thermal inertia effects, sea ice export. And so by comparing these 2 different sets of experiments, we can see what are those non-albedo effects of sea ice, and how does that impact Arctic warming. So what do we see in terms of near surface temperature for the Arctic? This is showing from 70 to 90 north for the non-land Arctic in different months of the year. On top are our ice experiments. This is standard runs that do have sea ice for an 1850 control climate and the doubling of CO2. And then on the bottom are the 2 experiments with no ice under 1850 and doubled CO2 conditions. So we can see that those no ice experiments are really cold because we've set the albedo of sea ice. So they're reflecting a lot of sunlight, but they have a really damped seasonal cycle. So again, the ocean is really slow to warm up and cool down seasonally. So when we have no ice and just the albedo effects of ice, we have this really small seasonal amplitude of near surface temperature. Whereas in our full ice experiments, that sea ice is quick to warm up and cool down seasonally, as you can see here with these really cold winter temperatures and much warmer summer temperatures near the freezing point. So that's one effect in our ice runs, is that we're increasing the seasonal amplitude of temperature compared to if we only have the albedo effects of sea ice. What does this mean when we go from 1850 to doubled CO2 conditions? I'm showing that here on the right. This is the near surface warming, again for the Arctic, for our doubled CO2 minus 1850 experiments in each month of the year. And we can see that we get kind of annually constant warming in our runs with only the albedo effects of sea ice loss. And then in the runs that include other ice effects, we damp warming in summertime. So much less warming when we include sea ice thermodynamics. So I think what's happening here is that our sea ice, again, has this small thermal inertia that allows for this huge seasonal amplitude and really warm summer temperatures in the mean state that are near the melting point. And so when we add extra energy for a doubling of CO2, we're just pouring that into latent heating of melting ice, and we're not actually able to warm the surface in summer. So we have really damped summer warming in that ice experiment, whereas in our experiments with no ice, we're able to have really cold summer temperatures with this smaller seasonal amplitude, and those can warm up more in our double CO2 run. Just to show the annual effect of including ice, we found that including these non-albedo ice effects reduces our annual mean warming by a negative 1.8 degrees Celsius. So a pretty big effect on annual mean warming. I'm going to look a little bit more into what mechanisms are driving that reduced annual warming. But yeah, the takeaway here is that sea ice thermal inertia increases the seasonal amplitude of temperature and reduces summer warming under increased CO2. So in order to look at these non-albedo ice effects, what's driving this annual warming, I'm just first going to give some background on one factor that will come into play, and that's the lapse rate feedback in the Arctic. So this is a schematic of sea ice in different months of the year in the Arctic, and the lapse rate feedback relies on having these really stable surface inversions in the Arctic where you have super cold temperatures, so that for some initial warming, you trap warming near the surface because you can't get that turbulent mixing. And then this surface trapped warming, in response to any kind of warming in the atmosphere, will have increased outgoing long-wave radiation. But because that warming is happening near the surface, that outgoing long-wave radiation from lower in the atmosphere gets more attenuated by greenhouse gases and clouds, and so there's less that's able to escape to space. So there's less efficient outwave, long-wave radiation damping of our surface warming. That gives extra surface warming. So this is a positive feedback in the Arctic, basically due to these really stable temperature conditions that support amplified surface warming. So how is that going to come into play? Here I'm calculating the role of different feedbacks, including the lapse rate feedback and heat transports, and how those contribute to warming under CO2 forcing in our ice experiment. On the x-axis are ice experiments, and then the no ice at albedo experiments on the y-axis. So if a factor is on this 1-to-1 line, it's contributing equally to warming in both of those cases. And if it's farther away from that line in the upper left triangle, it's contributing to more warming with only the albedo effects of sea ice, or damped warming when we include other effects of sea ice. And so we can see that one factor that stands out is this lapse rate feedback, and that's damping warming when we include ice thermodynamics. And I think that's, again, related to this thermal inertia of sea ice, where it's small, so we get this large seasonal amplitude of temperature, these warm summer temperatures that can't support those inversions that I showed in the last slide. So because we don't get these inversions in summertime, we can't have a positive lapse rate feedback. So the existence of ice leads to either a zero or slightly negative feedback in lapse rate feedback in summertime that damps, that leads to less summer warming. In contrast, if we only had the albedo effects of sea ice, we get these much colder summer temperatures because we have a large thermal inertia and are slow to warm up and cool down seasonally. So we actually can get a surface inversion in summertime with only the albedo effects of sea ice, and that allows for a lot of surface warming and a positive lapse rate feedback. So that's one factor that is reducing warming when we include sea ice thermodynamics, the lapse rate feedback. One other factor that pops out here is this purple term, the surface energy budget component, which is showing the role of the ocean in this. And as I showed earlier, we think that in the mean state, sea ice export leads to a net latent heat import, so that's a heating of the Arctic. But in the future, when you have less sea ice, there's less sea ice export, so less latent heat import. So that's a cooling effect due to just reduced sea ice export in the future. And we can see that in the ice run, this reduced sea ice export, this purple term, is giving us a cooling effect, whereas there's no effect when you have no ice, because there's no ice to export. So yeah, these were the two big factors that stood out, were sea ice thermal inertia and the lapse rate feedback, and also reduced sea ice export, and both of those are damping our annual mean warming when we include the full effects of sea ice. Just to put this in context of the albedo effects of sea ice, this plot, I've added one more set of experiments here where I have no ice at all, and I haven't done anything to prescribe albedo. And so when we compare these no ice runs to the runs that have no ice but do have albedo changes coming from sea ice, we can see the effect of those albedo changes on warming in the Arctic. And you can see that including these ice albedo feedback gives about a 5-degree warming, or increased warming. In yellow, that's the difference between the dotted and dashed lines. whereas, as I showed before, these other effects of sea ice reduce warming by about 2 degrees. So the takeaway is that non-albedo ice effects are offsetting about 1/3 of the ice albedo effect on Arctic warming. So a pretty sizable impact of these non-albedo effects of sea ice. That's kind of the first takeaway, that while the ice albedo feedback increases Arctic warming, sea ice thermal inertia and export changes reduce Arctic warming. And that's been thinking more about the annual mean cycle that we also saw these summer effects. But I'm going to dive more into seasonality in Arctic warming next, and I'll give a little background on some past mechanisms that people have proposed of how sea ice impacts seasonality and warming. One mechanism is seasonal ocean heat storage. So the idea is that as you lose sea ice in summer, you get increased solar input, you're absorbing more shortwave radiation, and then that gets outputted back to the atmosphere in early winter through increased turbulent heat fluxes, because that's when your atmosphere is colder and you have a bigger temperature difference to support those turbulent heat fluxes. I should say we're trying to understand this early winter peak in warming that we see when we do have sea ice in the Arctic. Why do we get this peak early winter warming under CO2 forcing? So one idea is that the seasonal ocean heat storage allows for peak early winter warming through these turbulent heat fluxes. Another thought that's related is that there are also ice insulation effects, where we also have thinning ice in early winter, and you get increased conductive heat flux through that thinning ice that also amplifies warming, especially in early winter, because that's when you have both cold atmospheric temperatures and thin ice conditions. So another possibility that I talked a little bit about already are these long-wave cloud and temperature feedbacks, like the lapse rate feedback. So these peak in wintertime because that's when you have those surface temperature inversions. And the idea is that these winter peaking feedbacks are producing winter peaking Arctic warming under CO2 forcing. The last mechanism that I'll talk more about here is increasing thermal inertia of the surface layer. And the idea there is that we start out with sea ice, which again is really slow to cool down, is really quick to warm up and cool down seasonally. It has a small thermal inertia, so it's cooling down a lot in early winter. And then when we melt that, when we replace frozen sea ice with open ocean, that has a much larger thermal inertia. It's slow to cool down in early winter. So just moving from this condition where you're quick to cool down in early winter to being slow to cool down means that you have a relative warming in early winter that could give you that peak warming. So I'll look at that mechanism too. It's really hard to pick these all apart in a global climate model that includes these all at the same time. So to look into this, I'm going to use idealized experiments in a single column sea ice model to try to isolate these different mechanisms. This sea ice model was created by Ian Eisenman and also John Metloffer, who, both Till and I worked with Ian at Scripps. And so it's evolving the surface enthalpy, which is proportional when there is sea ice and enthalpy is less than 0. It's proportional to the sea ice thickness. When enthalpy is greater than 0, there's open ocean, and it's proportional to the mixed layer temperature multiplied by this ocean heat capacity, determined by the mixed layer depth. So to change surface enthalpy, we have some different surface heat fluxes in the model. So there's solar forcing that depends on your surface albedo, outgoing long-wave radiation that's linearized. There's a basal heat flux that's just a constant, some ice export, and then we can increase the forcing from 0 to represent increased CO2 in the model. Just to note that the albedo in this model is varying smoothly from an ice albedo to an open ocean albedo as a function of the enthalpy. So how does surface temperature get determined? When we have enthalpy less than 0 and we have frozen ice, it's determined from a balance of the surface energy budget and conductive heat flux through ice. But if that would give temperatures greater than 0 when you still have ice, then the temperature is set to equal 0 while the ice melts until you have enthalpy greater than 0. And then surface temperature is proportional to the enthalpy divided by the heat capacity. So we're trying to use this model to understand the seasonality in Arctic warming. So it's important to know what in this model can contribute to that. It does include seasonally varying feedbacks, the Planck feedback and surface albedo feedbacks. It also has changes in ice insulation and conductive heat flux as sea ice thins. And then it has changes in surface thermal inertia as ice melts and exposes open ocean. It doesn't have a lot of other climate feedbacks, like the lobster feedback, or changes in poleward heat transport. So we expect that for a given forcing, there will be not as much warming in this model as in our global climate model. But we're hoping it will still be a useful tool here. So to look into that and see whether it will be useful, I'm going to see how it compares to a comprehensive climate model, CESM2. And here I'm showing surface temperature for a bunch of different experiments, or actually, sorry, just the pre-industrial control experiment in the lightest blue, and then this run different periods in this experiment where CO2 has been increased 1% per year up to a quadrupling and then held constant. So we have increasing CO2 conditions in our darker lines. And then on the bottom, we're looking at the anomalies in surface temperature for each of these periods compared to a pre-industrial control. I just wanted to point out some key features of this warming pattern. Also a note that I'm looking at 9D north here for better comparison with the single column model, which takes its parameters from the central Arctic, but we see a very similar pattern of warming if we also average from 70 to 90. So one key feature, as we saw before, is that warming peaks in early winter under increasing CO2 in this global climate model. As we continue to increase CO2 in these darker blue lines, that peak in warming shifts to late winter, to January, February. So we're seeing peak early winter shifting to late winter with increased CO2. So how does our single column model do in comparison? Here I'm showing a range of forcings in the single column model to show conditions ranging from frozen ice to open ocean when temperatures are greater than 0. And in the bottom, we're comparing each of these forcing experiments to a 0 forcing experiment. So we can see that despite not having a lot of the other factors that go into climate models, our single column model is able to capture this seasonal pattern of Arctic warming with peak early winter warming that shifts to a peak in late winter with increased forcing. So we think that this model, although it's a bit simpler, it will be a useful tool to pick apart what's driving this pattern, the seasonal pattern of warming. The first thing I did was to get rid of seasonality and feedbacks and see what happens. So I did that by using an annual mean Planck feedback and a constant ice albedo in these experiments. And we can see the main takeaway is that we still get seasonality and warming, these key features of peak early shifting to late winter warming, even without any seasonality and feedbacks. So it seems like something more fundamental is going on. One possibility, I'll just give a reminder that when temperatures are less than 0, we have frozen ice in the model, and when they're greater than 0, there's open ocean. So here in green, I've boxed the regime where we have frozen ice. Under those conditions, part of this seasonality and warming could be coming from conductive heat flux through thinning ice. And so to test that, I've set a constant ice depth in the conductive heat flux in this panel on the right. And when we do that, we get constant warming in different months over frozen ice. So that definitely checks out, including seasonality and conductive heat flux is supporting peak early winter warming over frozen ice. Again, because you have cold temperatures, cold surface temperatures, and also thin ice at that time of year that give you this early winter warming peak. So that's one factor that's going on over frozen ice. I think what's even more interesting in this panel to the right, though, is that even without any seasonality in warming over frozen ice, we still get seasonality in warming when we transition from frozen ice to open ocean, whether that happens in early winter or later on with more forcing when it happens in late winter. So it seems like there's something fundamental about the shift from frozen ice to open ocean that is driving this seasonality in Arctic warming. And that would be consistent with this thermal inertia idea. But I'm going to test that by explicitly modeling changes in thermal inertia. And we can do that by changing our single column model again. So in this case, I'm going to have no ice in the model and only an ocean mixed layer. So the temperature is proportional to the enthalpy divided by this effective heat capacity or thermal inertia. And we can control the thermal inertia by changing the mixed layer depth. So I'll show 3 different runs. Just to note that I, again, have gotten rid of anything else that could contribute to seasonality. There's no ice, so there's no conductive heat flux impact. And I've also gotten rid of seasonality in the Planck feedback here. And I'm using a constant ice albedo. But here are the experiments that I'll do. In one case, I have a really shallow mixed layer that's representing the small thermal inertia of frozen ice. So mixed layer depths of 1 meter. And then I have an experiment with a deep mixed layer representing the large thermal inertia of open ocean. And lastly, I'll have an experiment that is transitioning from this small mixed layer representing the small thermal inertia of frozen ice for enthalpy less than 0, and then a deeper mixed layer for enthalpy greater than or equal to 0. And again, that's trying to represent this transition from frozen ice to open ocean and differences in their thermal inertia. So what's the impact on surface warming here? Here I'm showing just that in the experiment with a shallow mixed layer representing the small thermal inertia of frozen ice, here's what surface temperatures look like for a range of forcings, and here's the anomaly in surface temperature compared to the 0 forcing scenario. We can see that with a small thermal inertia, as we saw before in our global climate model for frozen ice, you get this really quick seasonal heating and cooling, this really large seasonal amplitude of temperature, although we have no seasonality in warming in comparison to the 0 forcing scenario. In contrast, if we have a larger mixed layer depth representing the large thermal inertia of open ocean, the surface temperatures are much slower to warm up and cool down seasonally. And again, we don't have any seasonality in warming. Next, I'm going to oh yeah, sure.
And you also turned off the seasonality of the feedback results as well?
Yeah, exactly. They all have no seasonality feedback. Yeah, thanks. So in the next one, I'm going to allow for a transition from this small thermal inertia of frozen ice for enthalpy less than 0 or temperature less than 0 to the large thermal inertia of open ocean for enthalpy or temperature greater than 0. And so when we do that, we can see that as we increase our forcing, we're moving from frozen ice to open ocean, and that slows our seasonal heating and cooling rates. So where originally we had frozen ice in the lighter blue line that is cooling down really quickly in early winter, now we have open ocean that's very slow to cool down in early winter. And so we have this huge relative warming between the frozen ice and then with more forcing open ocean that gives us that peak early winter warming that we saw. And then later on, when that transition from ice to ocean happens in late winter, we get a late winter peak in warming. So just by modeling these changes in thermal inertia, we found that increasing the thermal inertia of the Arctic surface layer alone as we transition from frozen ice to open ocean can produce this seasonal pattern of Arctic warming. Great, that's kind of the takeaway from this first part, thinking about what impacts seasonality in Arctic warming, that there's
How much interannual variability is there in the transition from a 1 meter to a 50 meter deep mixed layer?
Yeah, I haven't included any kind of interannual variability in these runs. Guessing a lot in the Arctic, it's a really, got a lot of variability. I did do a bunch of sensitivity tests. Clearly these are like really idealized, and I'm just using like one mixed layer depth for ice and one for open ocean. So I tested how did our results vary if I use different mixed layer depths to represent open ocean, which is true, like mixed layer varies all over the Arctic. But it's not too sensitive to that because you can like get an expression for the phase shift as in temperature as a function of effective heat capacity, and it's like a tanh function, I think, that is it's sensitive to changes when you have a smaller values, but less sensitive for larger values of the mixed layer depth. So yeah, I think it could impact the timing a little bit in winter, like when you get that peak, your mixed layer depth could, but I think the main story will be the same.
Okay.
Yeah.
Thanks.
Yeah, for sure. Great, so the main point of this first part is that non-albedo effects of sea ice matter, especially this thermal inertia effect, both for annual and seasonality in Arctic warming. In the next part, I'm gonna move a little bit away from the Arctic and think more about the role of the Atlantic Meridional overturning circulation for uncertainty in near future warming. So as shown in this pretty simplified schematic, the AMOC is this system of ocean currents that brings warm surface water poleward, where it cools and gets saltier, and then sinks and brings colder water at depth back southward in the Atlantic. And so across the latest generation of climate models in UW-6, there's a really huge spread in the strength of the AMOC circulation in this pre-industrial control experiment. That's what's shown here. These are 28 models in UW-6. And there's also very large spread in the degree of their decline for an abrupt CO2 quadrupling. We can see that models that have a weaker AMOC in the mean state have less of a decline in blue, and those models also tend to have more global mean warming. But there are a lot of other factors that contribute to global mean warming, not just the AMOC, so a bit difficult to tease that apart just in these fully comprehensive model experiments. I wanted to also mention in the Arctic, for this talk I'm going to focus on the global mean effect, but there's even bigger effects in the Arctic. There's a better correlation in climate models between, for models with a weaker AMOC and smaller decline, they tend to have more Arctic warming, and if we average around year 100 in this plot with a 30-year average, you can see that models with a smaller AMOC decline tend to have a lot more Arctic warming. So it also looks like big impacts in the Arctic. But yeah, it looks like there's a ton of intermodal spread in AMOC, but the effect of that uncertainty in AMOC on uncertainty in near future warming has not yet been quantified. So my question here is, to what extent and through what mechanisms does AMOC impact uncertainty in near future warming? Here I'm again showing that range in AMOC declines among CMIP6 models, and then on top of that, I'm showing CESM2, one of those models, in the solid black line, which has one of the largest declines across CMIP6. And then in the dashed line is a new experiment that I've run where I'm controlling the strength of AMOC by removing fresh water. I'm doing a dehosing experiment, removing surface fresh water through the virtual salinity flux in the model. So removing that from the northern hemisphere high latitudes and adding it elsewhere around the globe so that we get a constant global mean salinity. But the effect is to give a stronger AMOC, less of an AMOC decline in CESM2 in our black dashed line. So the idea of these two experiments is to try to span a lot of this intermodal spread that we see across CMIP6 models and see how does that intermodal spread, if imposed in a single model in CESM2, how much does that impact warming and through what mechanisms? But first, I think one fair question is, how representative are these two experiments in a single model of spread across all of these different models in CMIP6, and especially in how these AMOC differences impact ocean heat uptake? So here I'm showing the anomaly in ocean to atmosphere heating. I'm going to show anomalies for our dehost experiment the last 30 years, presented around year 100, minus the 4x CO2 experiment, so a stronger AMOC. So for the ocean to atmosphere heating anomaly here, for our dehost 4x minus standard 4x CO2 experiment, we can see that a stronger AMOC leads to more northward ocean heat transport and ocean to atmosphere heating in the North Atlantic and high latitudes. And then on the right side, I'm showing just a regression for CMIP6 models of the anomalies for quadrupling CO2 compared to pre-inertial control anomalies in ocean to atmosphere heating regressed against that AMOC index change. And so this is also saying that models in CMIP6 that have a stronger AMOC or weaker, less of a decline, that produces more northward heat transport and ocean to atmosphere heating in a pattern that broadly matches what we found in our experiments. So we think that these experiments will be relevant for understanding how spread in AMOC in CMIP6 is impacting the atmosphere and the atmospheric warming. So what do we find for impacts on warming? Here I'm showing overlaid onto that global warming for all of the CMIP6 models in colors are two CESM2 experiments with standard 4 times CO2 and then with a stronger AMOC in the dashed line. We get about a degree more global warming. Yeah?
Sorry to interrupt. Just to clarify, the dehosing experiment, you're doing those in order to still retain the effects of global warming, but not the weakening of the AMOC? Is that right?
Exactly. Yeah. So we want to retain the effect. We still are running it under 4 times CO2 conditions, but we want to represent kind of this spread across CMIP6 where some of the models don't have as much of a weakening in AMOC. So we want to see in CESM2 if it was like those other models and didn't have a large AMOC decline,
okay.
how much would its warming have changed? Yeah.
Yeah, thank you.
So what do we find? For our dehost experiment, we get about a degree more global warming, which is 20% of the total intermodal spread in warming across CMIP6. I think that's a pretty sizable chunk of the total intermodal spread, which is impacted by a lot of other processes besides AMOC2. For the pattern of surface warming, we find that with a stronger AMOC in our DHOS minus 4 times CO2 experiments, we get more near surface warming, especially at high latitudes and in the North Atlantic. And yeah, I haven't shown this in this plot in the Arctic here, but we also find significantly more warming in the Arctic. That's about a third of the intermodal spread in the Arctic, so even more substantial effects in the Arctic in terms of impacts on near surface warming, as you can kind of see from this plot. So the rest of the talk is trying to understand why that is, what mechanisms are driving this change in near surface warming in our experiments. And we already looked at ocean to atmosphere heating. In the global mean, there's a more positive ocean to atmosphere heating in these transient runs, and we can see that the pattern of that lines up well with the pattern of where we get our largest, some of the largest anomalies in warming, where increased ocean to atmosphere heating is contributing to increased warming. So that's one mechanism that can contribute. Another one is changes in the net climate feedbacks in the atmosphere. So I'm defining climate feedbacks here using a regression of local radiation anomalies for our 4 times CO2 experiments compared to the pre-industrial control. So regressing those over the full period, the full 115 years. Regressing those radiation anomalies against global mean temperature anomalies. And then I'm here showing the difference in feedbacks between the 2 experiments. So our stronger AMOC experiment has a more positive net feedback globally, and that's especially coming from the North Atlantic. And that again could contribute to this greater near surface warming with a stronger AMOC. So I was interested in understanding why we get this feedback change. To look at that, we can decompose the net feedback using this radiative kernel method by Shell and Soden. We can decompose the net feedback into different individual climate feedbacks. Here I'm just again putting the net feedback change for our stronger AMOC experiment and also the near surface warming pattern. If we look at the water vapor and long wave cloud feedback changes, for our stronger AMOC experiment, we get this greater warming in the northern hemisphere, and it's well known that causes an ITCZ shift northward, and also Hadley cell shift northward, so that the upper branch of the Hadley cell can transport more potential energy southward and balance out, kind of compensate for this this imbalance in near surface warming. So with that northward ITCZ shift, we get a more positive water vapor and long wave cloud feedback in the northern tropics because we've transported, along with the ITCZ, all of that moisture and high cloud cover, and then the opposite in the southern tropics. And there, in addition to those dynamic effects, can be some thermodynamic effects just from the warming in the northern tropics and cooling in the southern tropics that amplifies this water vapor feedback. But it's clear that that's not the whole story. That's not giving us the main changes that we see in our net feedback. And what's doing that is the lapse rate and shortwave cloud feedbacks shown here in the bottom panel. So those are contributing most to our less negative feedback when AMOC is stronger. And mostly are coming from the North Atlantic, where we have a more positive feedbacks for both lapse rate and shortwave cloud in the North Atlantic. What's going on there is that our near surface warming is reducing our lower tropospheric stability. We're getting more warming near the surface than higher up, and that's giving us a more positive lapse rate feedback. And then both that surface warming and reduced stability allows for more entrainment from the free troposphere of dry air into the boundary layer, which gets rid of clouds and allows for more shortwave radiation to be absorbed and gives this more positive shortwave cloud feedback. So we've shown that with the cloud controlling factor analysis, where you can look at the effect of different factors like SSTs and estimated inversion strength on the cloud feedback. And those 2 things combined can reproduce this pattern of the cloud feedback, which is great. The kind of main takeaway here is that AMOC is controlling the strength of climate feedbacks, especially the lapse rate and shortwave cloud feedback. And this is really consistent with some past work in earlier generations of climate models that showed that clouds really amplify the effects of AMOC on the climate response. But here we've kind of done a full feedback decomposition and looked at the mechanisms more of that cloud feedback. I think one follow-up question is, if surface warming is really important for getting rid of clouds and giving us this more positive shortwave cloud feedback, how do we get that surface warming to begin with? To look into that, I did a mixed layer budget analysis that I'll kind of gloss over the details of, but This is basically a diagnostic to tell us how much each term in the surface energy budget is contributing to sea surface warming anomalies. So we can see that if we just look at the role of ocean heat transport in this first term on the left, that's kind of explaining most of our surface warming in the North Atlantic. We get that, as I showed before, more northward heat transport and ocean to atmosphere heating that's warming SSTs with a stronger AMOC. And then we saw that gets rid of cloud cover and leads to more incoming solar radiation. So we also get this huge contribution from increased net shortwave radiation at the surface, shown here. Those are kind of the two biggest factors. But then another interesting thing going on is that we have a wind evaporation SST feedback, where in response to some initial SST warming, we normally have a subtropical high pressure here, and our in response to this warming, we're actually weakening that, and we're getting reduced winds, near surface wind strength, shown here in these wind anomalies. And so with that reduced wind strength, we get less evaporative cooling, and so that leads to these positive anomalies in the latent heat flux from the wind changes in this positive wind evaporation SST feedback. So that's kind of a much smaller term, but it's important for bringing this warming down to the tropics. And it's not just in the North Atlantic, but it's like across the northern tropics as we get that ITCZ shift north and slowing of the winds. There's less evaporative cooling, which leads to extra warming in the northern tropics. So the main takeaway there is that ocean to atmosphere heating produces these North Atlantic SST changes with a stronger AMOC that get reinforced by cloud-induced changes in shortwave radiation and by the wind evaporation SST feedback. I have a couple follow-up questions before wrapping up. The first one is, how does these feedback changes we saw for one model, how does that compare to feedback differences across models in CNIP6 that are associated with differences in AMOC? So to look at that, here I'm first showing, just for our experiments, the lapse rate feedback and shortwave cloud feedback differences when we have a stronger AMOC. And then I'm now showing the regression across CNIP6 models of the lapse rate feedback against the AMOC anomalies. And I've normalized that by the AMOC change in my two experiments, the AMOC difference, so that we can get to the same units of watts per meter squared per Kelvin. But the main takeaway is that our lapse rate feedback with a stronger AMOC across UW-6 models, we get a similar pattern of a more positive lapse rate feedback in the North Atlantic, kind of matching what we saw in our experiments. And there's some differences in the Arctic. There's more going on across UW-6 models, and I think that's because there are bigger sea ice differences. So when you get a stronger AMOC across UW-6, that is helping to get rid of sea ice and then driving this more positive lapse rate feedback. Whereas in our CSM2 experiments, we have very little sea ice in either case, so there's not much going on with the lapse rate feedback in the Arctic. But overall similar in the North Atlantic, this lapse rate feedback pattern between our experiments and CNIP6. And then for the shortwave cloud feedback, here I'm again regressing that against the AMOC anomalies across CNIP6 models for CO2 quadrupling, and we see really similar patterns, again, where a stronger AMOC is associated with a more positive shortwave cloud feedback. There are some differences in the southern hemisphere especially, where there's some more negative cloud feedbacks associated with the stronger AMOC than in my two experiments. But I guess one thing to keep in mind is that that could be coming from the opposite direction of causality. Like it could be that these more negative cloud feedbacks produce a stronger AMOC rather than the AMOC producing negative cloud feedbacks, or there could be actual differences between our model and other UW-6 models. But yeah, overall, really similar patterns. So we think that these experiments are also relevant for understanding how spread in AMOC across UW-6 impacts spread in climate feedbacks. I'll just show an average for this region of the North Atlantic for the shortwave cloud and lapse rate feedbacks across, kind of looking at scatter plots of those feedbacks versus the AMOC decline in all the UW-6 models in gray. And then I'm adding my CSM2 experiments. I've snuck one more experiment that's kind of an intermediary decline experiment in there in black. But kind of this is just showing what the last slide showed, that a stronger AMOC or less of a decline supports a more positive shortwave cloud feedback, more positive lapse rate feedback, and more positive net feedback in the North Atlantic. both across MIP6 models and in our experiments. I think one other follow-up question, I'll just go back to this. I think this is like maybe somewhat surprising because there are huge differences in cloud physics across different models, so pretty cool that the AMOC is having such an influence across different models, even though they might also have differences coming from other factors. But I really focused on the North Atlantic, and that's where the local feedbacks are changing the most. But if we look at this in the context of other literature, and specifically this like Green's functions literature, others have found that SST changes in the Pacific, the tropical Pacific, those local SST changes have the biggest effect on global mean radiation. And so we might expect the global mean feedback to be most sensitive to changes in local Pacific SSTs in the tropical Pacific, whereas the sensitivity is pretty small in the North Atlantic. So how does this mesh with our experiments? Is the North Atlantic actually explaining the change in net feedback, or is that coming from some remote effects on the Pacific? Just to show again the pattern of SST anomalies for our stronger AMOC versus standard experiment, most of that warming is happening in the North Atlantic. So when we put those two things together, we can come up with how the actual SST warming in our experiments between for our stronger AMOC versus for our CO2, how that actual local sea surface warming impacts the global mean feedback. And we can see that it's mostly coming from the North Atlantic. That the actual SST changes in the North Atlantic are giving us the biggest effects on the global mean feedback, with smaller effects also coming from the North Pacific, and some negative effects on feedback from more tropical regions. But this is basically because that's where all the warming is happening, is in the North Atlantic. So when we combine that with even this weak sensitivity to local warming, that region is still having the biggest effect on the global mean net feedback, which is shown in this plot here. So takeaway there is that the less negative global feedback with a stronger AMOC is largely explained by North Atlantic sea surface warming. The last thing we wanted to do is try to think about the relative role of feedbacks versus ocean heat uptake. And we saw that those are like really interrelated because ocean heat uptake also impacts the feedbacks. But one first way of getting at this is just through a single layer energy balance model. Ideally, you'd want to run some more idealized experiments to try to split those two things up. But just using this single layer energy balance model, the surface temperature is going to depend on our ocean heat capacity and also on our forcing and our climate feedbacks. And so what we can do is we can reconstruct our temperature time series, our temperature anomalies for the quadrupling of CO2, just using the single layer model, and then we can swap different parameters. Like if we had only changed ocean heat capacity between our two experiments, or only changed the global climate feedback, what would be the impact on temperature? So that's the last thing I'll show. This is just showing the near surface warming for our standard 4 times CO2 experiment and the dehosed or stronger AMOC experiment, looking at those anomalies versus the pre-industrial control. For the actual warming and then our EBM reconstruction, and by construction they have to be the same. We're reproducing the actual warming with the EBM. So next I'm going to swap out those parameters. So we'll start from our standard 4 times CO2 run, but only use the net feedback or the heat capacity from our stronger AMOC run. And that's shown in these yellow and blue lines for just changing the feedback or the ocean heat capacity. And we can see that both matter in this simple model. Both are kind of contributing similarly to increasing temperature compared to our standard 4 times CO2 experiment. Again, would ideally want to use some more experiments to get at this, but this is suggesting that both feedbacks and ocean heat uptake are important. So that's kind of the takeaway from this second part, is that intermodal spread in AMOC imposed within a single model caused about 1/5 of the total intermodal spread in global warming by changing ocean heat uptake and the shortwave cloud feedback. And one upshot of that is that model uncertainty in global warming might be substantially reduced if we can constrain projections of AMOC. And that's all I have. So thanks so much.
Thank you, Lily. Any questions, as per usual, students first? Hamish, don't. Go for it.
I was really interested in your non-albedo ice impacts. And so your simulations, you're using double CO2 runs. Do you have an inclination if those numbers, I think it was a third less warming because of the non-albedo work in our current observed historical temperature changes? Like, are they directly applicable, or do you think those only kick in when you do get double CO2?
Yeah, that's a good question. I haven't looked at that. I would expect it not to be linear at all, or like it should be, depend on, I mean, we have bigger, like in a CO2 forcing run, you typically get like larger changes in sea ice to begin with, and then you lose your ice and get, less change over time. So, the effects of ice albedo should be muted over time, and but also those other effects of thermal inertia. So maybe the ratio of like the impact of each of those might still remain similar, regardless of your forcing. I don't know, but yeah, I do. Yeah, definitely. I think it might depend on the forcing amount. Yeah, that's a good question. Just like maybe in a 1% per year CO2 run or something.
Yeah.
Good one.
Sorry.
Yeah.
It's okay.
Great talk, Lily, as always. I have a simple question about the dehosing simulations and experiments you ran. When you're dehosing, do you see, because it's still a quadruple CO2 simulation, do you see any changes in sea ice in those runs? And because you mentioned that SimM6 has some weird sea ice going on, but could some of those results be explained by some weird behavior in sea ice as well?
Yeah, for sure. Yeah, it's super dependent on sea ice. So in our, I wish I had my sea ice plot, but I'll just go up to the warming figure to read this. Yeah, so we found that, so when you dehose, you get extra warming, and that leads to increased warming in the Arctic, but our standard 4 times CO2 run already had almost all of its sea ice gone. And so when we get this extra warming in the Arctic, but we don't get those positive ice albedo feedbacks because there's no sea ice there. So we don't have as much of that as we would if there was sea ice. So yeah, definitely sea ice is like mediating the effect in the Arctic. And if I was doing this with like less of a strong forcing and there was still sea ice to lose, I would expect an even bigger sensitivity of Arctic warming to the AMOC decline. I'm like collaborating with some folks who run EC Earth 3, and that model has the opposite situation. It has a kind of weak AMOC decline, and then they've run some hosing experiments to give it a bigger AMOC decline, so that cools the Arctic, and then you can grow sea ice, and then you do have these really strong sea ice feedbacks that amplify that cooling. So there's a much bigger sensitivity of Arctic temperature to AMOC in that model than for this direction of, so I think sea ice totally matters for the sensitivity, to Arctic warmth, to AMOC.
Clark.
So in your dehose simulation, you showed that some of the winds in the subpolar region are reduced. Did you see a reduction in that subpolar gyre as well as a result?
Yeah, I haven't looked at the, maybe these are the winds that you're talking about. I haven't looked at that. I've looked at like sea level pressure and which is related, I guess, but no, haven't done that. That would be good to, I think that's like one fair question with this experimental design too, is like we're imposing the freshwater forcing to try to get at AMOC, but it will also impact gyre strength, and that could also be producing some of our temperature effects. I think others have tried to quantify that. You can like quantify how much heat transport is accomplished by AMOC versus gyre changes, and have found that it's mostly AMOC changes in these hosing experiments that are like doing things, but I think that would be a good thing to double check on whether, is that kind of what you're getting at, whether like gyre changes are impacting warming too, or?
Sort of. Just like trying to figure out like what happens to the gyres under warming.
Yeah, I haven't looked at that, but probably should.
Anyone else? Yes, John.
Great talk, Lily. I'm sorry it'll be a naive question, but my eye was drawn to the temperature gradient at the southern edge of the Sahara that
Oh,
is
wow.
induced by the changes that you're talking about.
Yeah.
And then there's warm sea surface temperatures in the western part of the Atlantic Basin. I'm wondering if there's increased tropical cyclone activity that comes out of changes in the sea ice in the North Atlantic or in the strength of the AMOC.
Yeah, I also haven't looked at tropical cyclone activity, but I do know another NOAA Climate and Global Change fellow, Jordan Jones, I think, that's her whole postdoc project, is looking at how Atlantic warming is impacting cyclone intensity and frequency. So based on that being her whole project, I would guess that there's some important effects.
Yeah.
But yeah.
Because the thing that catches my eye is the African easterly jet should be stronger under these conditions. And
Gotcha.
I don't know if it reaches a threshold, sort of like the Pacific jet does in the wintertime, where if it gets too strong, the waves don't really unfold when they get out of the jet and you get a suppression. But I don't know if this pushes it over the edge or if it just makes it stronger
Yeah.
as a quantity.
Yeah, that's a great question. I should maybe check in with Jordan, who has a lot of these diagnostics set up for cyclones already in model experiments. So yeah, that'd be great to see.
I think in general, right, the teleconnections from Arctic changes to lower latitudes is still not really understood.
Mm.
Yeah.
Yeah, that just stands out as a potential synoptic example that just hits you right across the face.
Yeah, I know when thinking about the impact of the Arctic warming on lower latitudes, that it ends up being a more complicated picture because of the 3D structure of warming. So I guess I'm only showing the near surface warming effects, and I'm not sure how that is communicated to the upper troposphere, which probably has a big effect on this.
I presume it goes at least to 700 millibars in one way, shape, or form. Maybe not higher than that, but it doesn't have to for the African easterly jet.
Yeah.
Fairly low level feature.
Okay, cool.
Thanks.
Yeah.
Anyone else? I was going to ask you, also probably naive somehow. So you're talking about how global warming is amplified essentially if you have the stronger your AMOC, the more you're warming the globe, right?
Right.
But if you're reducing your AMOC as you warm the globe, right, you might have a cooling in the North Atlantic area.
Yeah.
Is that right?
Mm-hmm. Right.
How are the changes induced in the region by the changes in the AMOC compared to the background global warming signal? Are they the same? Do they cancel out in certain cases, or is one much larger than the other?
Yeah, so you're thinking of maybe just subtracting the 4x CO2 minus, just kind of looking at, the pattern of warming too for, I don't have those plots here. It's a similar pattern. We know that there's Arctic amplified warming under CO2 forcing, so at least that much is similar. But there's also warming in the southern hemisphere, so that's going to be a reversal of the of that pattern.
I think part of the reason why I'm asking is because I'm going to teach the day after tomorrow. Tomorrow I will teach the day after tomorrow,
Okay,
right?
that makes more sense.
In my global warming class, and the idea there is, your AMOC shuts down and you're plunging the world into into an ice age, and I'm always wondering because your AMOC, if it shuts down, you're inducing some cooling, but it's shutting down because the globe is warming, right? So you must have an offset of those.
I think this might get at that question a little bit. We get about a degree of extra warming if we don't have, this is almost getting rid of the AMOC decline entirely.
Okay.
About a degree of extra warming in this 4 times CO2 run. But the warming itself is 6 to 8 degrees. So it's a small fraction of the total global warming.
Right.
But it is a larger fraction of the spread in global warming. So I think still an important process, but not a doomsday, I don't think.
Right. So we're not dropping Western Europe by 10 degrees, right? In this case, you're dropping it by 1 degree, but you're having 6 degrees of warming.
Yeah,
Something
exactly.
like that. Okay.
Yeah.
All right, then, that's reassuring for Europe.
Yeah.
I have a question. Okay, so in the dehosing, are you hosing the entire time or unhosing the entire time?
Yeah, it's a constant 0.5 sphere drop removal.
Per year or?
Yeah.
Okay.
All the time. Yeah.
So, have you looked to see at all, like, how much the warming itself might reduce the strength of the AMOC? Because if it's very warm in the North Atlantic, then the water's not able to get very cold, so it might not sink.
Yeah.
So, yeah, have you
Yeah.
looked into that?
A little bit. I started thinking a little bit about this because when I was trying to, had to do some playing around to get the right AMOC decline that I wanted. So I did some other runs with like a 0.25 surge of dehosing, and it was very nonlinear. Like the amount of warming that we get for that 0.25 dehosing was like up here somewhere. So I think, yeah, it would be interesting to follow up and think about.
Like dehose and then stop the dehosing and then see how it reacts from there.
Yeah, but one person's work that might be interesting to you is Camille, I think her last name's Lee, or no, Henkel, maybe. She's I got them confused, but she's now a postdoc at UW with CC Bits, and looked at how AMOC impacts kind of depend on the amount of forcing that you're prescribing. Like, are you ramping up CO2 or are you quadrupling CO2? And I think that might be kind of related to your question.
Okay.
Yeah, check. Sorry.
Camille Henkel.
Henkel, yeah, sorry, I always forget.
Leek is the one in France.
Yeah. There's a lot of Camille.
All right. Well, we're right on time. Thank you all. Let's give